What happens to the coil on the right if we connect an AC source to the coil on the left? The voltage of the source is shown for us. Now the source voltage is going to match the inductor voltage here. They would have the same basic graph shape. So if, for example, this is the negative side of the source and this is the positive side, then at the same time this will be the positive side of the coil and this will be the negative side. Their voltages will match. But one thing that won't match is the current. For any coil, the current is going to be 90 degrees out of phase with the voltage across that coil. Now with capacitors, we saw that current leads voltage. With inductors, it's the opposite. Voltage has to lead current. This means that when our voltage is at a peak, the current needs to be at 0. And then the current needs to hit its peak after the voltage has. So the shape that we're looking for is this. We'll find that the current is 90 degrees out of phase with the voltage, and current lags the voltage by 90 degrees. The magnetic flux that we get in the secondary coil is determined by the current in the primary coil. For that reason, they'll have the same graph and they'll be in phase. Now, when it comes to the voltage induced in the secondary coil, it will have to follow Faraday's law. The full form of this, when we have more than one coil though, we should put an N in to the formula. N stands for the number of turns in the coil. What this says is that when the magnetic flux is changing the most, that's when we have the most induced voltage. So we would actually want to look at the slope of the graph for that. The steeper the slope is, the more the flux is changing. And this is the steepest point. Right here, when we're at a peak, it's not steep at all. Which means it's changing the most here, and it's not changing at all at the peak. What ends up happening is we get the same type of graph that we had for the original voltage, but because of the negative here, I'm going to switch the direction.